Hello everyone, my name is Shridhar. I am assistant professor in the department of ISC, BMSIT Bangalore. I am going to discuss module 5 of discrete mathematical structures, graph theory. So, contents of this PPT I have taken from Discrete and Combinatorial Mathematics by Rafal P. Grimaldi and Discrete Math by R.S. Chang. For today's session, I am going to discuss what is a graph, applications of graph, what is a simple graph, and how do you calculate in degree and out degree, and some special edges like parallel edges and loops. So, once I complete this session, so you will be able to gain the knowledge on what is graph, degree of graph, and simple and weighted graphs. So, we will begin with a simple definition. So, what is a graph? So, in a graph can be described as a pictorial representation of set of objects where some pairs of objects are connected by links. These interconnected objects are represented by points termed as vertices, and links that connect the vertices are called as edges. This is an example. You can see that the diagram. Okay, this is a graph. So, this graph has set of vertices. So, you can see these are the vertices x, vertex v, vertex w, vertex u, vertex z, y, and s. So, it has a set of vertices. So, we can define the set of vertices as order of graph. Okay, we can write order of a graph as $v equal to the number of vertices in the graph. So, here the number of vertices are 7, and the number of edges that we can represent as size of graph. So, size of graph is E. So, in this figure we have 13 edges. Okay. So, we have represented here the order of vertices in this graph G and the size of graph, that is the number of edges. And also we can define a graph as a pair of vertices and edges. Here vertices is the set of all the vertices in this graph G, and edges are the set of all the edges of graph G. Now, we will see some of the applications where we can use the graph. So, in the graph can be used for various numerous applications. Okay. So, some of the applications include a social network. Okay. You can see that many social media applications, they use the concepts of graph theory. Say Twitter, Snapchat, Facebook, Instagram, Telegram, all these social media applications, they use the concept of graph theory in their applications. So, let us take an example of Facebook. So, you know that in a Facebook we have a user, and each user has a set of friends, right, and these friends have their own friends, and some of the friends of the user and a friend are common. So, how Facebook represents all this information? So, the Facebook uses the concept of graph theory to represent all this data into their server. So, what happens? They will create one user. So, they treat that user as a vertex in a graph. So, once he becomes a friend to the another person, so there is a relationship between the user and that friend. So, this relationship they will represent by using an edge. So, you can see that here is an vertex. So, this is a user. So, if he has a relationship with another user, so that is represented by an edge. That is represented by an edge. Okay. So, this is how they use the graph theory concepts for their applications. Next, we have a circuit design where we can use the concept of graph theory. So, consider when you are developing a PCB. PCB is a printed circuit board, okay, where lot of electronic components are connected with the conducting path to form a electronic circuit. Okay. So, this electronic component should be connected, one electronic component should be connected to the another component, so that proper flow of electric current occurs, so that we will get the desirable output. So, in order to realize that, so first we will design a graph. So, each electronic component is taken as a vertex, and the in order to connect one electronic component to the another electronic component, we use the edges. So, this is the design that first we draw using the graph concept, and this graph concept is used for their PCB design. Okay. And another application, say for example we have the electricity distribution. Okay, so we have we need to supply the powers to all the households. So during that with that example, we can optimally connect the power generators to each of the houses. So this we can represent using a graph. Another example include like route map. Okay, I think most of you have used this application, okay, in order to find a path from one city to another city. So here a city is considered as one vertex and the other city is considered as another vertex. So if there is a path, that is a road connecting between the city 1 and city 2, then that can be represented by using a edge. Okay, so with that concept we can find optimal path in order to reach from city 1 to city 2. So we can work on with some graph algorithms so that the path is optimal from path 1 to city 1 to city 2. Okay. And another example include say network topology. Okay, so internet itself is considered as one graph, network graph. Okay, where we have set of routers. These routers are connected to the other routers. So all this can be represented by using the graph concepts. Okay, there are not we have so many other applications where we can use the applications. We can use the graph theory, say for example artificial neural networks, right, or to form a knowledge graph. So these are some of the examples where we can use the concept of graph. Let us discuss, as I told, the relationship can be established using an edge. Okay, so the edge connects a pair of vertices. So you can see this in the figure. So we have a vertex V and vertex W. So these vertices are connected via edge. Okay, this is an edge, and edge is represented as a V, W. So it is the edge is connected from V to W, and E said to if we connect an edge from V to W, then we can say that edge is said to be incident on vertex V as well as edge is incident on to the vertex W. And if we consider any vertex which does not have any incident edge, we can call it as a isolated vertex. You can see in this figure. So this vertex is not connected with any edges, so we can call it as a isolated vertex. Now we will discuss some special edges and special graphs we have in a graph. Okay, let us consider this figure. Here, what is the order of graph here? So order of graph is the number of vertices. You can see we have the order of graph is 5. Okay, and what is the order of size of graph? Size of graph is the number of edges. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So size of graph is 9. Okay, and I am going to discuss about some special edges in this graph. So you have seen that an edge connects a pair of vertices. You can see here. So we have a vertex A and vertex B. You can see that there are two edges connected for the vertex pair A and B. Okay, so these edges E1 and E2, we call it as a parallel edges. Okay, we call it as a parallel edges because if there are more than one edge connecting between pair of vertices A and B, so these are called as parallel edges. And next is a loop. A loop is an edge that starts and ends at the same vertex, that we call it as a loop. You can see here, this is edge E3. So this edge starts with a vertex D and again it ends with a edge vertex D. So such type of edges we call it as a loop. Okay, and if we have a graph, so we can represent one vertex as a graph. So this graph with only one vertex where there are no edges, we can call it as a empty graph. Okay, and in the graph if we have only one vertex, we can call it as a trivial graph. So next we will discuss about directed and undirected graph. You can see that in this figure, so edges have direction. So if we have a direction for the edge, the graph that consists of edges with the direction, we call it as a digraph or a directed graph. Okay. So here we have an edge going from A to B, again an edge from B to C and edge from A to C. So this graph, this type of graph, we call it as a directed graph. And next what we have is a undirected graph where the edges does not have any direction. So such type of graphs we call it as a undirected graph. Okay. You can see that in this figure we have a graph of 3 edges. So A to B, B to C and C to A. Yeah. Suppose if we have an edge that connected from we have an edge connecting between 2 vertices, say U and V. Okay. We call it, and there is a direction for each edge, then we can call this particular graph by using some namings. Say for example, here if we consider A and B as U and V, we can say that U is called the initial vertex of E and V is the terminating vertex of E. Say here, so we have an edge that is connecting from A to B. So here the A is considered as the source vertex or initial vertex, okay, and B is called as the terminating vertex. Okay. A is called as source vertex and B is called as terminating vertex. Again we can consider this edge. So here we have B as a source vertex and C as a terminating vertex, and whatever the edge here, say E1. So this edge is said to be an incident on U. Okay. The edge is said to be an incident from U and to be incident on V. Here the edge is incident on A and edge is incident to be on B. And similarly you can say that U is an adjacent to V. Here in this example, A is adjacent to B and B is adjacent from A. Okay. That is how we can represent with a graph. And next is degree of vertices. Okay. So here the degree of a vertex in a simple graph with n number of vertices, the degree of vertex is given as degree of V. So this degree of V is always less than or equal to n minus 1. So n is the number of vertices in a graph. So here what is the number of vertices? So the number of vertices is 5. So always the degree should be less than degree of V should be always less than or equal to n minus 1. So we have 5 number of vertices, so it should be always less than or equal to 5. So degree of vertex can be defined as the number of edges incident on a particular vertex. Okay. Number of edges incident on a particular vertex. Say if I consider this example, okay, this vertex if I take, so how many vertices are incident on this particular vertex? There are no incident edge. Okay, there are no incident edge. Here the edge is not there. So the number of vertices we have here is the number of incident vertices for vertex V is 0. Okay, so the degree of this particular vertex is 0. Okay. So in general, if we do not have any direction on the edge, we can calculate 2 types of degrees. One is in degree. So if we have direction on the edge, we can call 2 types of degrees. So one is in degree and another one is out. We can call it as in degree and out degree. Okay. So the in degree we can say that the number of edges which are coming into the vertex. So that we can call it as a in degree. Say in this example, the in degree of vertex 3 is, so it can be represented as in degree vertex 3. So the in degree of this vertex is 1 because we have only one edge coming into the vertex 3. Okay. So the in degree of vertex V3 is 1. Similarly, what is the in degree of V5? So, the in degree of vertex V5 is 2. As you can see, there are 2 edges that are coming to the vertex 5. Okay. Similarly, we can say what is the in degree of vertex V4? So, in degree of vertex V4 is 1, right. So, this is how we need to calculate the in degree. Now, let us see how we calculate the out degree. So, next is out degree. So, out degree can be defined as the number of edges which are going out from the vertex V. So, in this graph you can see that let us calculate what is the out degree of vertex V3. So, here the out degree says the number of edges which are going out of the vertex. So, in this figure you can see that the out degree of vertex V3 is 2, because we have these are the two vertex which are going away from the vertex V3. Okay. Let us see what is the out degree of this vertex. The out degree of this vertex is vertex 4 is 1, because we have only one edge which is going out of the vertex V4. So, this is how we need to calculate the in degree and out degree of a vertex. Okay. So, this is how we can represent. So, we have set of vertex V1, V2, V3 and V4, V5, and we will calculate the in degree and out degree. So, in degree of vertex is 0, because there are no edges coming to the vertex V1. So, in degree is 0, in degree of V2 is 1, we have one edge here, similarly others. So, this is how we will calculate in degree and out degree. Suppose a graph is does not have any direction on the edge. Okay. If this graph does not have any direction on edge, so what we call it as degree of vertices. So, there is no in degree and out degree, because directions are not there on the edge. So, here in that case, so we have the degree of vertex V1 is 1, because one edge is incident on vertex V1, okay, and degree of vertex V2 is 2, because two edges are incident on vertex V2, and similarly the degree of vertex V5 is 2, because two vertices are incident on the vertex V5. Okay. Now, let us see what is a simple graph and what is a weighted graph. Here a simple graph, we say a graph G is a simple graph if it does not have any loops or a parallel edges. So, I have told what is a loop and parallel edges. So, parallel edges are the one if there are more than one edge for a pair of vertices, we call it as a parallel edge, and loop if the edge start at the same vertex and end at the same vertex, we call it as a loop. So, if in the graph, in a simple graph, there are no loops or a parallel edges, then that particular graph we can call it as a simple graph. Okay. Example is here. So, you can see that there are no loops or parallel edges in this particular graph. Next is weighted graph. So, if we assign a weight for each of the edges in a graph, then that particular graph we can call it as a weighted graph. So, you can see that a weight is assigned to edge that is connecting between V1 and V2. Okay. So, what is the weight of this particular edge? The weight of this particular edge is 4. Okay, 4. Now, consider edge that is between V4 and V2. So, what is the weight associated with that particular edge? It is 4. Okay. So, this type of graph where we are assigning a particular weight to an edge is called as a weighted graph. Okay. So, these are some of the basic terminologies and definitions for graphs. So, we will cover next topic, that is walk, trial, path. So, how to calculate a walk, a trial and a path in a graph. So, let us see, we have a graph here. So, we have 5 vertices and 6 edges in a graph. We will see how to calculate a walk, trial and a path. So, walk is an alternate sequence of finite vertices and edges. So, we can consider a walk, say if I start from a particular vertex. We start a walk from a particular vertex. Say if I start a walk from one vertex and I want to reach onto the other vertex, say I want to reach the vertex C. So, we can have a path say from A to B, from A to B and from B to D, B to D and from D to A back and again A to B and then B to C. So, we can see this has one walk. So, it consisting of alternate sequence of vertices and edges. Okay. This sequence can be a finite number of vertices and edges. So, that we can call it as a walk. Okay. Say another example for walk is say B. If I start from B, then I will go to C, then I will go to D, okay, then I will go to E and I will go to A. So, this is another walk starting from B and ending with a A. So, it consisting of alternate sequences of vertices and edges. Next we have so what is the length of this particular path? Okay, what is the length of this particular walk? So, it is the total number of edges that we have in this particular walk. Say in this example we have 1, 2, 3, 4, 5. So, we have 5 edges here. So, the length of this walk is 5. Okay. So, this is how we can calculate length of a walk. Now, we will see what is a trial. Okay. So, in a trial if no edges are repeated, okay, in a walk if no edges are repeated, then we can call that as a trial. Say for example, here we start with the vertex A and reach to the vertex D. So, during this walk if we does not cross on the same edge more than once, then we can call it as a trial. Say for example, here, so we are starting from A, so we are starting from A and going to B, okay, and then we are reaching B and again C, we are reaching to C and again from C to D and again D to E and from E to B and from B to E, B to D, B to D. As you can see that we have not visited the same edge more than once. So, such type of walk we can call it as a trial. Okay. So, let us see another example with respect to trial. So, what is the we can have more number of trials in a graph. Okay. Let us say another example. So, I will go with a B, then I will have D, from D to C and again C to B. So, this is example of another example for trial. Okay. Now, let us see what is a path. So, in case of trial, as we see there is no repetition of edge. So, in case of path there will be no repetition of edge as well as no repetition of vertices, then we can call it as a path. You can see in this example we have a path from A to E. So, we will start with a vertex A, we will reach to B and from B to C and again from C to D and from D to E. So, in this path you can see that there are no edges repeated or no vertices repeated. So, such type of walk we can call it as a path. Okay. Such type of walk we can call it as a path. So, let us see another example. So, I will start with the C, okay. I will start with C, D, C, D, B, A. So, we can call this as a path because there are no edges and vertices repeated. Now, let us see what is a closed walk and open walk. Okay. Now, as I said, walk is a sequence of alternate sequence of vertices and edges. So, this walk can be characterized into two walks. So, one is a open walk and another one is a closed walk. So, what is an open walk? So, if we start to walk from one particular vertex, and if we reach to the another vertex which is not same as the source vertex, then such type of walk we call it as a open walk. Okay, open walk. Now, let us see an example for the open walk. So, if I start from B, okay, I will reach to C, then I will reach to D. So, this is an example for the open walk. So, there is another type of walk, we call it as a closed walk. In the closed walk, what happens? If we start with a vertex B, then we will reach to the same vertex. Then such type of walk we call it as a closed walk. Here is an example. So, let us say we will start from A. Okay, A we are starting. So, we reach to B, then C, then D, and then A. As you can see, so I have started a walk from A, I reach to B, B to C, C to D, and again I am going back to the same vertex. So, such type of walk we can call it as a closed walk. Okay. So, if we start with a vertex X and if we reach a vertex Y which is not an X, then such type of a walk we can call it as a open walk, and if we reach to the same vertex, then we call it as a closed walk. Okay. Now you have seen what is a trial. Now you have seen what is a trial. So, in a trial the edges are not repeated. In the trial the edges are not repeated, and in the path the vertices as well as edges are not repeated. Now, see what is a circuit. Okay. What is a circuit? A circuit is nothing but a closed trial. Okay. Yeah. Closed trial we call it as a circuit. So, what is a trial? Trial, here the edges are not repeated, and if we start with the same vertex and reach to the same vertex, then we call it as a circuit. So, here is an example. So, we start with the vertex A and reach to B, C, D, B, E, D, and again back to A, then we call it as a circuit. Okay. And what is a closed path? So, closed path, if we start with the same vertex and reach to the same vertex without repeating any vertices and edges, we call it as a cycle. Okay. So, that particular closed path we can call it as a cycle. Here is an example. So, you can see that I am starting with a vertex A and ending with the same vertex A. So, in between we have alternate sequence of vertices and edges. So, these vertices and edges are not repeated. So, such type of walk we can call it as a closed path, which is a cycle. Okay. So, we can have any number of cycles in a graph. Say here is another example. So, I will start with a B, okay, and I will go to E, then I will reach D and again back to B. So, this is called as one cycle. So, there is a cycle from B to E to D and B. So, this is an example for the cycle. So, with this you can say that in a graph, if vertices are repeated, okay, and edges are repeated, and if it is an open walk, that if it is open, then we can call it as a walk, okay, open walk. If vertices are repeated and edges are repeated and it is a closed, that is the source vertex and destination vertex are same, then we can call it as a closed walk. Okay. And if now let us see the third, if vertices are repeated and edges are not repeated and it is a open walk, then we can call it as a trial. Okay. Now, see if vertices are repeated and edges are not repeated, and if it is a closed walk, then we can call it as a circuit. Okay. So, in case of path, the vertices are not repeated and edges are also not repeated and it is a open walk, then we can call it as a path. Again, if no vertices are repeated and no edges are repeated and it is a closed walk, then we can call it as a cycle. So, these are the basic terminologies what we have in a graph. Okay. One is open walk, closed walk, trial, circuit, path and a cycle. Let us see with an example. So, here is an example. So, what we have is vertices A, B, C, D, E, F, G and H, okay. And these vertices are connected by edges. So, now determine which of the following sequences in the graph are walk, closed trial, path and cycle. So, let us consider this walk, okay, from B to E, E to F and F to G. So, is it a walk? Is it a walk? Let us see. So, we are starting from B, okay. So, what is a walk? So, it is an alternate sequence of vertices and edges. So, we will start with the B, okay, and then E, yes, there is a edge connecting to E, and next is F, yes, there is an edge connecting E to F, and from F to we have G. So, G we have G here, there is no edge connected from F to G. So, that is why it cannot be a walk, okay. So, it cannot be a walk. Is it a closed walk? Since it is not a walk, then it obviously it will not be a closed walk or closed trial, path or a cycle. So, what is the answer? So, it is not any of this. So, answer is none. Now, let us see. Now, see this path, this walk that is starting from A, starting from A, we are reaching to B, then B to E, then E to F, and then we have D, then D to A, yeah. So, now you can see that this particular vertex is repeated. So, if the vertices are repeated, so it cannot be a what cycle or a path. So, it has to be either trail or a circuit. So, now D, okay. Now, I reach to A, again A to C and C to D and D to B. So, we are starting from a vertex A and we are reaching to vertex B. So, in between we have the repetition of vertices. So, obviously, this cannot be a circuit. So, this has to be a trial, okay. So, this is a trial because the vertices A, B and D are repeated. Now, let us see another walk D, F, D. So, we are starting with a D, we are reaching with F and again we are reaching back to D. So, here we can see that no vertices are repeated and edges are repeated. So, such type of walk we can call it as closed walk because we are starting with the vertex T and reaching with the same vertex without any repetition of edges. So, we can call it as a closed walk. So, this closed walk it is also called as a cycle because there is no repetition of edges and repetition of vertices. Now, let us see another walk A, we are starting with A to B, okay, from B to E and E to F and F to D and D to C and C to A. So, as you can see, we have not repeated any of the edges or any of the vertices and we are beginning with the A and reaching to the same vertex. So, this is an example for it is a closed path. If it is a closed path, then we call it as a cycle. So, this is an example for a cycle. Now, let us see what is this. So, we are starting with A, okay, A to C, C to D, D to F, then F to E, then E to B, then B to D, and again D to A. So, we have repetition of the edge vertex D, okay. So, we have visited the vertex D to repeated and A also repeated. So, obviously this cannot be a cycle because vertices are repeated. So, it has to be a circuit, okay, because we are starting with the same vertex and reaching to the same vertex without repeating any edge. So, such type of walk we can call it as a circuit. Now, let us say another example. So, we have A to G, a walk from A, then I am reaching to B, then B to D, then D to F and F to E and then E to G. So, here there are no repetition of edges and vertices and I am starting with the A and reaching to G. So, since there is no repeated vertices and repeated edges, we can call it as a path, okay, because we are starting with the vertex A and reaching to vertex G. So, we are not reaching back to the same vertex. So, it has to be a open walk, and if there are no repetition of edges and vertices, we can call it as a path. Okay, let us see, this is an example. Or determine a walk from A to F. So, walk it is an alternate sequence of vertices and edges. So, I need a walk from source vertex A and destination vertex as F. Okay. So, what is the answer? So, we will start with the A, then reach B, then E, then F. So, this is one example for the walk starting from A and reaching to F. So, there may be an alternate sequence, say I will write from, I will start with the A to B, okay, B to E and E to G and again F. So, this is another example for the walk starting from A to F. So, this is one example, A to B, B to C, C to A, A to B, E to F. Now, determine a path from A to F. So, as I told, when I say a path, so edges and vertices should not be repeated. Okay. So, we will start from A, then B, then E, then F. As you can see, there are no repetition of edges or vertices. So, it is an example for the path. Now, let us see, determine a trail, not a path from B to D. So, I have to determine a trail. Okay, what do you mean by a trail? So, trail we have no repetition of edges, but vertices can be repeated. So, that is what we want. We do not want a path, we want a trail. Okay. So, here is an example. So, I will start with the vertex B and I will reach to E, from E to G, E to G, again G to F and F to E and E to D. So, as you can see that, so vertices is repeated. So, which vertex is repeated? So, vertex E is repeated. So, that is why it cannot be a path. So, it is a trail. Now, determine a circuit, not a cycle from B to B. So, in case of circuit, no edges should be repeated, but vertex can be repeated. So, you can see that in this example, what is the repetition of vertex we have? So, we have vertex E is repeated. So, this is an example for the circuit. So, what is a closed trial? So, if it is a closed trial, that is the starting vertex and terminating vertex are same, we can call it as a circuit. Okay. Now, see this example. So, we have a graph. So, here we need to determine a walk from S to A, which is not a trial. Okay. We need a walk from S to A, which is not a trial. So, when I say it is not a trial, it means that, so edges can be repeated. Okay. So, here is an example. So, we will start with the H, E, we have to make sure that one of the edge is repeated. So, I will reach to E, E to D, E to D, again D to C, then C to E, C to E and E to D. So, you can see I am going back to E to D. So, this edge is repeated. Okay. Again from D to B and B to A. So, since edges are repeated here, so this cannot be a trial. So, So, it is not a trial, but it is a walk, as I can reach from H to A with alternate sequence of vertices and edges. So, now determine a circuit from E to E. So, circuit, so no edges should be repeated, but have to reach to the same vertex E, right. So, here is an example, E to C, E to C, C to D, then D to E, then E to G, E to G, and G to F, again F to E. So, the vertices are repeated, but edges are not repeated. Now, determine a cycle from B to B. Here in this example, so we should not repeat any vertices or any edge. So, you can see we have 2 cycles here. So, starting from B, okay, B to D, okay, B to D, D to E, D to E, and E to C, and C to B. So, this is one cycle, and we have another cycle, B to D, B to D, D to C, and C to B. So, since the start and vertex are the same vertex and there are no repetition of edges or vertices, we can call it as a cycle. So, I hope you understood how to, from a graph, how to determine a walk, a trial, and a path. Thank you.